Hi everyone, my name is Tudor. I'm a PhD student at Imperial College London, and I'm happy to present you today our recent research results on how spectral normalization improves performance in non-stationary setups. The presentation today is the result of collaboration between members of Clopath lab at Imperial College London and others from Technical University of Cluj-Napoca, UCL, Bitdefender, and DeepMind. Now, before talking about spectral normalization, let me place this work in the context of our workshop. And for that, let's just revisit what we mean by continual learning. There are multiple definitions for continual learning, as there are multiple benchmarks for it. And what all of these have in common is that a continual learning agent must be able to learn from non-stationary data. What we mean by that is that the distribution of the training examples changes to training. Now, as there are many definitions, there are many metrics or many expectations we would have from such an agent. Arguably the most important, and for sure the most studied, is the ability to cope with catastrophic forgetting. What I mean by that, we refer to that unpleasant property of neural networks to forget old knowledge as soon as they are being trained on new data, on a new task. Now, continual learning, it's not only about catastrophic forgetting. There are other features we would want such an agent to have. And for example, we would like a continual learning agent to be able to exploit the common structure between the tasks in the sequence he has to learn and exhibit some forms of forward or backward transfer. What we mean by that is that we expect our agents to learn faster and faster as they see more and more data, as they are being trained on more and more tasks. At the same time, we would like, if there is a connection between new data and old data, for such an agent to be able to connect them and to arrive at more general hypotheses that could improve performance on all tasks, even if data corresponding to it won't be revisited. Now, before going to the last point, let's imagine a very simple solution to catastrophic forgetting. Imagine that you just freeze the weights. No synapses change from now on. Now, that would be an ideal solution for catastrophic forgetting, but at the same time, that agent would be useless from a continual learning point of view. And that's because no further knowledge could be acquired. So, this last point, plasticity or adaptability, points to something that usually goes against avoiding forgetting. It's something that in neuroscience it's called the plasticity stability dilemma. And from what we know, there's always a trade-off that has to be made between forgetting and acquiring new knowledge. But acquiring new knowledge is a problem itself, right? Because the neural networks, let's say, that are at the core of such an agent don't start from a random initialization. And maybe this initialization, this point in the parameter space we are trying now to learn a new task from might not be as ideal or as good as a random one. So where are we going with this is we claim that actually studying the capacity of an agent to adapt to a new task under non-stationary data, of course, is a problem that it's worth studying in itself. So, more than that, we claim that spectral normalization is a good regularizer for such problems, and it's a useful addition for whenever agents rely on training neural networks. Now, let me point to what we actually refer to when we talk about adaptability and plasticity, because it's not always about the capacity to get 100% accuracy on the training set. It also matters how you do that. How well does the solution you arrive at generalizes? So imagine this setup proposed by Ash and Adams, where you train residual neural nets on CIFAR10. And plotted with blue here, we have a standard training process where you start from some random initialization and you train the model until convergence. And we see that the model gets to 100% accuracy on train. That's zero training loss. While the performance on the test set, of course, it's lower than that. So that's the performance you'd get if you just train from scratch on the full training data. Now, in the second setup, the one plotted with orange, imagine that you just train for a couple of epochs, or until convergence, in this case, on half of the data, right? And then, from that point 0, you fine-tune the model you arrived at on the full training set. So what happens here in the second part, in the right part of the plot, it's similar or identical for the two processes. The only difference is in the starting point, right? For the blue line, we had a random starting point, and here we had a we had parameters pre-trained on half of the data. Now, contrary to our expectations, this second setup, where we had this non-stationarity, generalizes worse. So even if in this case, in which the data used here is not on a different domain or picked in such a way in order to make training harder after, it's actually a subset of the data you're using in the second part. And in this case, it seems that non-stationarity affects the final generalization. Now, what we changed here was the inputs. But imagine a second setup where we would change the labels assigned to the examples instead. So, in this setup, we again compare a simple convolutional neural net trained on CIFAR10, and that would be what happens with solid lines, right? We plot here for two optimizers. So with solid line, we have on the bottom row the test accuracy for various convolutional neural nets while being trained on CIFAR10, right? As we see, the model in this case is not regularized. It gets to 100% accuracy on the training data. Now, in the second setup, the one marked with dashed lines, what we did was to change the training labels during the 300 epochs. So we started with a random assignment of labels for all the examples in the training set, and we incrementally corrected them until in the last epochs, in the last couple of epochs, the training data would be the original one. Okay, so when we arrive here at the end of the 300 epochs at 100% accuracy on the training set, we mean that we are 100% accuracy on the original training data. So what should we observe here is that under this non-stationary regime, there is a difference in the way the solution generalizes compared with the baseline. So there's a significant performance loss induced by the non-stationarity. Now, if we apply spectral normalization, which is the subject of today's talk, we see that this helps in recovering some of the generalization loss, the generalization gap. And this spectral normalization helps more in the non-stationary setup than it does for the baseline. So it's not that impressive when you apply spectral normalization in the stationary case as it is in the non-stationary one. Now, we would expect the same to happen if dropout or some form of weight decay would be added here, right? But what's interesting with spectral normalization is that if we were to zoom in a bit, right, in this region where we plot the training accuracy, we would see that actually these trials where we used spectral normalization adapt faster. So these experiments, these neural networks get 100% training accuracy much faster than the baseline. So as opposed to what would happen with dropout or weight decay, where those regularizers would slow down training, in this case training speed is not affected, but what you get as a bonus is a better generalization performance. Spectral normalization is not new to machine learning. It has been proposed as a regularizer for multiple times for all flavors of machine learning, including supervised learning, where it was used for image classification. Cook et al. Reported here that there's a small benefit from applying spectral normalization, but you have to be careful to the Lipschitz constant that you choose. Also, you've just seen that example with the non-stationary case again on CFAR10, and there's also known that when training generative adversarial networks, applying spectral normalization on the discriminator improves the final performance. And in the second part of this talk, I'm just gonna tell you how we applied spectral normalization in value-based deep reinforcement learning and what we got out of that. At the same time, there was this work from Björk et al., which also applied spectral normalization in a deep reinforcement learning setup, but in a policy gradient in this case. So what all these successful setups have in common, the ones in which spectral normalization seems to bring significant improvements? Well, they're all examples of non-stationarity. And before explaining how that really works in reinforcement learning, let me start with the results that we got, because this is quite interesting and gives a preview on our method. So what we have here is a plot with the mean human normalized score on the well-known Atari benchmark, and our baseline with blue is the DQN agent. Now all the other lines correspond to DQN agents for which we apply spectral normalization on a single linear layer in the estimator. So all these lines here are way better than the baseline, right, in terms of performance, and you can get them by simply normalizing a single layer in your estimator, nothing else. Now, if that convinces you to listen to me for the next couple of minutes, let me first revisit reinforcement learning as a general framework and explain where does the non-stationarity come from in this case. So in such setups, we have an agent which behaves in an environment, and by behaving we mean it needs to decide on an action, either from a continuous or a discrete space. And after performing that action, the environment changes, or some internal state of the agent, but let's say the whole ensemble jumps to a new state. And the state is perceived by the agent, or parts of it, and also the agent perceives some reward, which might be zero or might be more informative. And the agent again takes an action, and this happens in a loop, right? Now, the distribution of states the agent visits is actually a function, right, not only of the environment transitions, but actually of the agent's policy as well. And the agent changes the distribution of the states seen by changing its policy. Now, in the case of a DQN agent, which is just a deep learning variant of Q-learning, such an agent would use a memory, and usually without this memory you're not able to train the agent. Now, the whole purpose of this memory is to reduce the non-stationarity in the data seen by the agent. So for Atari, for example, we would store here the last 1 million transitions. Now, our baseline, our work were two agents. One was the DQN agents we just talked about, and the second was the simplest categorical version of it, C51. C51 differs from DQN in the fact that its output for a state action pair, it's not just a single value, but actually a categorical distribution over possible returns. Now, before describing our method and the results we got, let me revisit the principles from which spectral normalization has been derived. So we are sometimes interested in measuring the Lipschitz constant of a function, and this is just a number that represents an upper bound of the slope of the function over all its domain or some domain of interest. So basically, when a function is k Lipschitz, we know that between any pair of points, the functions cannot go more than this k slope would permit. Now, without going into much detail, for linear projections of this form, where you take some inputs and multiply them with some matrix A, let's say, we have a proxy to the k Lipschitz constant, to the Lipschitz constant, which is given by the spectral radius of the network. So when we try to use this in a more general observation and try to restrict the Lipschitz constant for a full neural network, we take into account that the Lipschitz constant of a composition of functions is just the product of all the individual Lipschitz constants, and for some nonlinearities we know it. We know that it's 1 for max pooling or Redus, for example, and convolutions, the linear layers, have simple methods to compute it based on this result we mentioned on the last slide, meaning we compute the spectral radius. Now, computing the spectral radius of a matrix might be costly, but not if the matrix changes slightly from one step to the next one, as it usually happens as we are using small learning rates. And that allows us to do just a couple, maybe just one step of power iteration, and always have this estimation of the spectral norm available. Now, when we normalize the weights, we just divide the original parameters of the network to this number, right? And we use the resulting matrix instead of the original parameters in doing the linear projection. Now, for convolutional layers, things are a bit more complicated, but there are ways in which there are similar ways in which you compute the spectral norm. Now, prior to our work, spectral normalization would be applied by dividing each layer to each matrix in the network by its spectral norm, and basically restricting the Lipschitz constant of the full network. Now, what we did differently was to normalize just a subset of the layers, and that proved to be beneficial. Now, in terms of results, again, in this Atari benchmark, we report here the human normalized score, and by applying this method, right, again for a single layer on top of C51, right, we basically got results which surpass the performance of Rainbow, which is an agent that puts together a lot of algorithmic improvements, a lot of tricks that are known to help for value-based DRL. Now, we studied a bit more the effects of spectral normalization and how robust it is to different changes in the hyperparameters or of the architectures. And to conclude many experiments that we did, it seems that spectral normalization shines when you have larger architectures, either wider or deeper. So we asked ourselves, okay, what's the reason, what are the means to which spectral normalization improves performance, right, in reinforcement learning? And one of the simplest and reasonable hypotheses was that it's about smoothness, and we actually get smoother optimizers because that's what you would get if you were to apply spectral normalization on the full estimator. So in our case, we just applied it to one layer. We saw that actually there's no consistent correlation between the smoothness that the final estimators got and the performance of them. So it seems that smoothness does not explain performance. Therefore, we tried to ask the question from an optimization perspective. So our hypothesis that I'm gonna go into next was that maybe what spectral normalization changes is the optimization dynamics. So in what follows, I'm going to detail how we started from spectral normalization and incrementally isolated more and more the scaling effects spectral normalization has on the gradients or on the optimization steps. So based on these approximations, we are going to propose a couple of optimizers or schedulers and compare their performance with the original spectral normalization method. Just to give a preview, we will arrive at 3 different optimizers, and it seems that all of them recover most of the performance of spectral normalization. Actually, there are some extra benefits I will detail later. Our first observation was that what spectral normalization almost does is to scale the activations of a layer, right? That would happen if we were to scale the bias term as well. So what we did first was to scale the bias terms in such a way that the activations on each layer are basically just scaled with a number, and that number is the inverse of the spectral norm. So to simplify things, we just consider all the spectral norms, right, of the layers we want to apply the method to. We took their product and took the inverse of that number, and we directly scaled the outputs. So we have this first approximation, which we call div out, in which we divide the outputs by the product of the spectral norms. And that was our first approximation. And then we thought, okay, but how does that affect the gradients? And what we did next was to isolate the scaling effect spectral normalization has on the on the gradients, and instead of dividing the outputs, we would now divide the gradients by that same number, the product of the spectral already considered. And again, this scheduler preserves the performance gain of spectral normalization. Moreover, we observe that this scheduler is actually a bit more robust to the choice of layer you would normalize. Now, last, what we did was to take the most common optimizer, which is Adam, and under some mild assumptions that the different spectral norms won't change that much from one optimization step to the other, we arrived at this approximation of the optimization step in which you would scale the dampening term, right, the epsilon term, by the again, that product of spectral norms. And basically we arrived at this scheduler which, considering that the norms usually increase during training, just change the way the optimizer behaves from standard Adam optimizer to a stochastic gradient descent with momentum flavor. Now, all these schedulers seem to work, and there are cases for larger architectures which are normalized on a larger subset of layers, in which actually dividing the gradients or modulating the epsilon term in Adam brings performance when spectral normalization itself would fail. So all these seem to work, and actually work better in some cases than spectral normalization itself. What we would conclude from here is that the ways in which spectral normalization helps is by changing the optimization dynamics and by modulating the optimization steps. Now, at the same time with our work, there was this paper published in which Björk and others from Cornell University would apply spectral normalization on policy gradient methods, and also report important improvements over baseline. Now, to conclude this talk, what we argued for here is that spectral normalization is a useful regularizer in non-stationary setups, but we are still left with the question: if there is something spectral normalization corrects, or there is something spectral normalization fixes, what is that? We don't know yet. So thank you for your attention, and I'm happy to answer any potential questions. Thank you very much.